Let's begin. Welcome back after the exam. I'll give you a quick reminder. We were doing hypothesis testing, and we make an assumption about something that we know about the population. Again, I'll give you the example of the fair coin. I give you a coin. I tell you the coin is fair, because that's what you would expect. And then you flip it 100 times, and you get 70 heads. Is this consistent with the coin being fair? No, you're most likely going to say, no, the coin is not fair because I got 70 heads. But what if you got 52 heads? Then probably the coin is fair, and that's just a result of randomness. That's what hypothesis testing is doing. As usual, we are looking at two population parameters, the mean and the variance. Okay? And which distribution to use to do your statistics tests depends on whether you know the population standard deviation or not. If you know the population standard deviation, for the mean, we use the normal distribution. If we don't know the standard deviation, we use the student t-distribution. For the variances, when we're doing hypothesis testing or any testing on variances, we use the chi-square distribution. And a special case on proportions, we always use the normal distribution because the standard deviation doesn't matter. In that case, it's deduced from the population. So we're going to do hypothesis testing on all four of these things. Means with a known standard deviation, means with an unknown standard deviation, proportions, and variances. All right, and you'll see the thing repeats over and over again. And I'll give you a table similar to the one I gave you on confidence intervals. This diagram, this chart about what statistic to use, what test statistics, so what z-score or t-score or p-score or chi-squared score. Well, z-score, there's no p-score, it's a z-score. So in the case where we know the standard deviation, this is the z-score that we know we want to compute from the sample. We can compute this. You know the sample mean. You know you have an assumption about the population mean, which we call the null hypothesis in that case. We know sigma about the population, we know the sample size, and you compute this statistic. And then there were two ways of testing whether a hypothesis, whether the null hypothesis is, we fail to reject it or we reject the null hypothesis. And the two approaches were a rejection region based on where your sample statistic lies. Is it in the tails, too far in the tails or not? Now, how far do you want to be out in the tails? That's dictated by your significance level, okay, which is called alpha, which is 1 minus the confidence level. Typically, alpha is 10% or 5%, so that determines how extreme you are in the tails, such that if you get a result in those tails, then your assumption about the population is wrong, okay? So you reject the null. If your sample falls outside the tails, inside the distribution, then you fail to reject the null hypothesis. And so that's the rejection region approach. We distinguish between a left-tailed, a right-tailed test, and a two-tailed test. We haven't done the two-tailed test, and I know it's kind of still fuzzy in your head. We will get to that in one example. You'll be able to see what that means. And with the rejection region, so let me go back to the hypothesis. The null hypothesis is always a statement of equality. You're saying the mean value of the population, I assume the mean value is equal to some mu0, and then your alternative hypothesis is either that the actual population mean is less than that, greater than that, or not equal to that. If it's less than that value, the less than mu0, then you do a left-tail test. If it's greater, then you do a right-tail test. And if it's not equal, you do a two-tail, what we call a two-tail test. And you either do a rejection region or a p-value approach. With the p-value, you calculate the probability of, if it's a left-tail test, the probability that your test statistic is less than that. So you get the cumulative to the left. And if you're doing a right-tail test, you do the probability of the cumulative to the right. If it's a two-tailed test, you're going to add the two probabilities. So that's kind of the one that's least clear, which we'll address in an example. Then if your p-value is less than your significance level, you reject the null hypothesis. In terms of rejection regions, this means that your sample is so far in the tails, it's inside that pink region that we defined, you reject the null. Otherwise, you fail to reject the null. And so we did this first example And you can review it. And we built a spreadsheet together. We started building a spreadsheet. So I want you to pull that out. Okay, so let me see. This was the one, right? So do you have the right-tailed as well? Do you have the right-tailed test? Yeah. Okay, we did the right-tail as well. Okay, because I remember this is where we stopped. I don't think we did the right-tail test, a test with a right-tail example. Did we do the confidence intervals? Do you have the confidence intervals there? Yes, we did the confidence. Okay, so yes, we did those things already. So you can review that. You can go ahead and review those. So yes, we did this example, I remember, for the women doing the master's degree thing. So let's jump to a two-tail example, and that will serve as a good example. We'll do it also in Google Sheets, okay? So with the two-tail test, a recent study showed that the mean number of children born to women in Europe is 1.5. Like, obviously, you can't have a child and a half, right? But like, this is just the 1 or 2 children. A Global Watch group claims that, like, what's half a person? Is it like split like symmetrically, or like like a mermaid, like a mermaid person, or like a inverted I don't know. Anyway, so a Global Watch group claims that German women have a mean fertility rate that is different from the mean for all of Europe. Okay, so our null hypothesis is that the average number of children born to all women in Europe, including Germany, is 1.5 child per woman. Okay, but this group says no, German women are different. We don't know if it's more or less. We don't know if they claim it's just different. Okay, neither more than 1.5 nor less than 1.5. We don't know, but we know it's different than that. And to test this claim, the group did a simple random sample of 128 German women and found that they had a mean fertility rate of 1.4 children. Now that's harder, like 40% of a person. How do you cut that? Like, and then what do you do with the other 60%? So, and a mean fertility rate of 1.4 children per woman. Okay, so that's our sample. That's our X bar. The population standard deviation is assumed to be 0.8. Okay, and that's also children per woman. And is there sufficient evidence to support the claim made by the Global Watch group at a 90% confidence level? So we have all the information. We have the population sigma, we have the sample X bar mean, we have the population assumed mean, which is our null hypothesis. We have the sample size 128. Confidence level is 90%. This means our significance level is 10% or 0.1. So we first state the null and the alternative hypotheses. The null hypothesis is always a statement, an equality statement. That's mu equal 1.5. The alternative hypothesis is either less, greater, or not equal to this same number. These numbers are always the same in a hypothesis test, okay? So once you figure this out, you put that here and then determine, are you doing a greater than, a less than, or not equal to? They didn't say it's more or less. They said it's not 1.5. So we can only assume that they're indicating a not equal to, okay? So that's our alternative hypothesis. Our alpha is 0.1. So everything, we do the same here. We compute the test statistic. We know sigma. So we get our test statistic as a z-score, which is sample mean minus assumed population mean over sigma over square root of n. And you do all of this, you get minus 1.41 for our z-statistic test. Okay. So next, we need to make a decision. And this is a not equal to situation, which means we have what's called a two-tailed test. In the one-tailed test, it was easy. You either go less than or greater than. With the not equal to, you have to split your rejection region into 2 regions. So we have a single alpha value, but because this is not equal to, it means we need to check whether this test statistic is not in either tail. Okay? And what do you do in that case? You have alpha, one value for alpha. What you do is split it equally in half. You say, I'm going to do half of the rejection region on the left tail and half of the rejection region on the right tail. That's the only difference. So when you go for a two-tailed test, your alpha is split into two because you want half of it in the left tail, half of it on the right tail, okay? Because it's not equal to, it's not less than, not greater than, it's just not equal to. So you have two rejection regions, but they're split in half between with alpha, okay? So then you determine, so you take this alpha over 2, you get your z-score for this alpha over 2, which is here minus 1.645. So this is the reverse lookup. And because this distribution is symmetric, this is automatically 1.645. And so you know these are your rejection regions. This is your test statistic. It's not in those regions. Okay? So it means we fail to reject the null hypothesis. Okay? So our result from the sample is not so extreme to say that German women do not have 1.5, we fail to reject it, do not have 1.5 children per woman, okay? So they still part of the European statistic, okay? Now with the p-values, what you need to do, you have to add up the probabilities that you're either less than minus 1.41 and greater than 1.41, okay? So that gives you your p-value, right? That's the only difference that that changes when you're doing a two-tail, okay? So with the one tail, we said it's either, if it's less than, you take the probability of less than that test statistic. So the entire area to the left, okay? So if this were a single tail test, you would take this entire area, that would be your p-value, and then if your p-value is less than alpha, you reject. If it's greater, you fail to reject. In this case, with the two-tail, because there is symmetry, either less than or greater than, you have to take the symmetric value of this, which is 1.41. You take the area to the left of this, the area to the right of this, and you add up. Okay, you add both of those up. And if that sum is less than alpha, then you reject. If it's greater than alpha, you fail to reject. Okay? That's the only difference when you have the two-tail distribution. Now, because this is symmetric, you only have to calculate that area once, to the left, right, and then you multiply by 2. So in this case, the area to the left of our test statistic or to the right of our test statistic, either minus 1.41 or 1.41, that area is 0.0793, okay? And then you multiply that by 2, so that gives you both of them, and gives you 0.1586, which is greater than our alpha, which was 0.1, so therefore we fail to reject the null hypothesis, okay? So let's do this in Excel or Google Sheets. Okay, so if we followed correctly, you should have roughly what we got up here, correct? I hope so. Okay, go away. So let's see, second here, we'll just zoom in. Nope, 125, okay. So if you remember when we built this spreadsheet, we had, this was the input that's given to us, the assumed mean of the population, that's our null hypothesis, the sample mean, which is x bar, the population sigma, which is known, because here we're doing mean hypothesis tests on means with a known sigma. Sample size is also given, significance level alpha. This is a calculated value. So all of these are inputs here, and everything else is calculated, so you can lock those up if you want in Google, lock these cells so you don't mess with them. This is simply just x bar minus mu over sigma by square root of n, okay? So for the left-tailed, we did these critical values for the rejection regions, right? So it was either critical value on the left, critical value on the right, and you notice they're symmetric, okay? Because this is a symmetric distribution. The normal distribution is symmetric. So whether you're doing a left or a right tail distribution, it's the same thing. Now for the two-tailed distribution, I can also calculate a critical value, which is going to be based on alpha over 2. Agreed? So for the left-tailed here, I'm going to pick the one on the left. This was norm.s.inverse of this significance level, right? Now I'm going to do that, take that, I'm going to copy it, just going to put here norm.s.inverse, okay? But I'm going to do alpha over 2, okay? So that gives me my my z alpha over, my minus z alpha over 2, okay? So that gives me the point on the left, the rejection region on the left tail, which also corresponds to the rejection region on the right tail, which would be 2.578. So I don't need to mention that. I'm just going to pick the one to the left. It's not going to matter in the calculation. Okay? So let's punch in the numbers for this example that we just did. Let me see. Hypothesis test. All right. So we had our null hypothesis was 1.5 children per woman. Our X bar was 1.4 children per woman. The population sigma was 0.8 child. Can you say 0.8 children? 0.8. Can you say 0? You can't say 0.8 children because 0.8 is less than 1, right? It's 0.8 child. Like 80% of a child, right? 80% of a child. Population sigma. That's just weird. Sample size 128. Okay, significance level is 0. No, the significance level was 0.1, right? 10%. Okay, so it gives me the sample statistic as we calculated here. This is, if we were doing a left tail, this would be it. A right tail, this would be it. We're not doing left or right. We're gonna be doing a two-tailed. Okay. So now, if my calculations are correct, yep, I got 1.645 for the minus 1.645 and 1.645. So this is the critical value. If you're thinking about the rejection region, this is the point where if your statistic falls below it, or on the right side, if it falls above it, then you reject, right? Because there's a symmetric value on the right side, which is plus 1.645, right? So let me show you on the slides, right? In my spreadsheet, I only calculated this guy, but I know in my mind that there's also a corresponding image of this on the right side. If my z statistic falls in this region, we reject the null hypothesis. Okay, but we're going to be doing it based on p-values, which is, again, the more likely thing to encounter in real life. So now for the z values, for the p-value, we need to we need to add up, okay, the 2 of the area to the left of this guy, or 2 of the area to the right of this guy, right? Or the area to the left of this negative value and the area to the right of its positive version. So again, let me show you in the keynote what this looks like. So this is for the p-value, you focus on your test statistic. You draw the line, you calculate the area to the left if you're doing a left tail, the area to the right if you're doing a right tail. If you're doing a two-tail, you take the mirror image of this, so there's a 1.41 here, and you calculate the area to the left and the area to the right of this. But they're equal, right? So you only have to do the area to the left of this guy, for example. Okay? All right, so let's see how we're going to do this. Let me see. Distribution. Okay, so what I'm going to do here, I'm going to say this is equal to norm.s.distribution. Okay, what does this give me? If I pick this is going to give me the standard normal cumulative distribution function for a specified value. So this is giving me the area to the left of a given value. Okay? Now, I want to make sure that I'm picking the negative z statistic. Okay? Now here we were fortunate that my sample statistic was negative. So this will just work. But what if my sample statistic was positive? Yes. Yes, thank you, Alexandra. You got it. Okay. So would you mind explaining that to the class now? Because it's really yes. Yes. So to circumvent this problem, we're going to take the absolute value of the sample statistic to make it always positive, and then multiply it by a negative sign so that we know we're picking the value to the left. And then take the area from the left to that point, multiply by 2. That gives us the p-value, okay? So what we would do, we say minus absolute value of this guy, parentheses, parentheses, and we need to multiply by 2. So that gives me my p-value. So this is p-value, right? It's 0.1572, etc. Okay? And finally, I just copy this, whether we fail to reject or reject. I'm just going to copy it. Okay, and it's going to be, instead of F3, is going to be G3. So now if my p-value is less than my significance level, I reject. If it's greater, I fail to reject. Okay? I fail to reject. Now, for my confidence interval, again, it's the same thing, okay? But it's going to be based on Z alpha over 2, not Z star. It's going to be based on a different value, okay? So what I'm going to do here, okay, I'm going to take, so remember the Z score was, the error was the critical Z value times sigma over square root of n, right? So this would be equal to my Z value, but I'm going to put it, my critical Z value, but I'm going to put it, I'm going to put it in absolute value, so I get a positive value for convenience. Okay, so Z value times sigma, okay, over square root of the sample size, 128, correct? Okay, so that gives me 0.1163 for the error. And then I can create here a confidence interval for a two-tailed test, two-tailed. Here I had mu plus or minus this error. Here I'm going to have mu. I'm going to have, so I should have equal to this x bar minus this value and x bar plus this value. Okay? Pardon me? This one? X bar minus E, X bar plus E. Okay, so now my confidence interval is from 1.3 to 1.5. My sample mean was 1.4. It falls in that confidence interval. It's not outside it, so yeah, it is part of the population. It's part of the error of estimating the population. So we fail to reject the null hypothesis. This is further confirmation. Okay, if you messed up one of those, if they're inconsistent, then you have an error somewhere. Okay? We'll repeat this now with the t distribution. So it'll be the same thing, and then you'll get another example of doing a two-tailed distribution. Okay. Go away. Jeez. Okay, it wants to keep coming here, so I'll just leave it. Okay. Next, we move to an unknown sigma, which is the more realistic case. Again, we're doing hypothesis tests on the mean. With unknown sigma, we know what to do. We're going to estimate sigma from the sample variance or the sample standard deviation. And by doing that, we introduce an error as well. And therefore, we have to use the student t distribution. So we will do exactly the same thing, but instead of a z distribution, we're going to do a t distribution. Okay? So, same as before, rinse and repeat, but replace the normal distribution with a t distribution. We have time to go through all of the examples, so we'll do that. So when we're doing a hypothesis test on a mean with an unknown standard population standard deviation, we will be using a t-score. X bar is the sample mean. Mu is going to be our null hypothesis, the assumed population mean. S will be the standard deviation deduced from the sample. And square root, and n is the sample size. Okay, so we've replaced sigma with s, the estimate from the sample standard deviation. But in this case, we also need a degrees of freedom to define the t distribution, and that's, as usual, sample size minus 1. Okay, so when you punch in the numbers to get the reverse t-score, etc., we need to use n minus 1. Now, we reject the null if our t statistic is less than the critical value. If we're doing a left tail test. For a right tail test, we reject it if it's above the critical value. And for a two tail test, we have to do the same thing if your t statistic, if your sample statistic falls either in the left tail or in the right tail. Okay? And the t distribution is symmetric, thankfully. So we replicate the same things we did with the normal distribution. The only thing that will change this will be the chi-square distribution. Because it's not symmetric, we have to do a little bit more work there. And the same idea for the p-value applies. If the p-value, which is the area either to the left, to the right, or in the two regions for your t statistic, okay? If that's less than alpha, we reject the null. If it's greater than alpha, we fail to reject the null. We don't have sufficient, it's very likely for this to occur, in other words. It's likely to get 60 heads even on a fair coin, right? Based on your significance level. Okay, so we will start with an example. Again, these are just lifted from your textbook. So we start with this one. Nurses in a large teaching hospital have complained for many years that they are overworked and understaffed. They don't have to complain. I mean, you can tell. Like you go visit the clinic recently or any time. It's insane how overworked they are. In fact, I have one of the so my youngest son. I probably should take this off of YouTube. Okay, so my youngest son, but I'm not gonna name names. So my youngest son, it's common when babies are born, they get a bacterial, like a fungal infection, like on the lip and the tongue. It's called like oral thrush. I think it's fungal, and it's very common. Like, well, pretty much. I don't know the statistics. A lot of babies get, like all the babies I've known in my circle have had it. And so there's a little kind of annoying medicine you have to put in, and it tastes very gross. But I have to taste everything like I give to my kids, make sure it's not going to kill me first. And so, I'm going to make sure that, they're going to be okay. So it just tastes very weird. But then we go to the pharmacy, and this was during COVID. Like he was born like 2 weeks into the shutdown. In April, it was really bad, and so everybody was understaffed. Everything was scrambling. You had to like wear a hazmat suit to go to the clinic and hospital and whatever. So we called the doctor. We spoke to this attending physician, and he was completely spaced out. And I could tell, like, hey, and like he's either drunk or he's just so overworked, which I think was the case, probably pulling like a 72-hour shift or something. So he sends the prescription. We go to this compounding pharmacy in Sandy, and I go up and then, hey, I'm picking up a prescription. So the guy gives me the medicine, and the dosage was like 850 milligrams per liter or something. And that's like extreme, super bug doses with amoxicillin or something like that. And I'm like, hey man, can you like check this? This is for my 2 months. Yeah, that's weird. So they call the doctor, and the guy comes out and is like, yeah, he was completely wasted. So they had to talk to another doctor and check. It was 10% of that dosage. So thankfully we caught that. But imagine, if I didn't know what to read, right? If I didn't know that this didn't make sense, which is the case for many people, like, not well-versed. I'm not even well-versed in medicine. It's just like I read a lot of this stuff, right? But if you overwork your doctors and physicians, it's going to result in bad things happening, okay? The pharmacist was like, you have to sue the hospital. I was like, I'm not going to sue anyone, man. Thank God we're okay. Thank God we caught it. Let's just move on with life. Anyway, but So yes, they are overworked. We'll see what the hypothesis test says here. And if it disagrees with me, it's absolutely wrong then, because they are overworked, right? So, okay, so the consensus among the nursing staff is that the mean number of patients per nurse each shift is 8 patients, okay? The mean number per, okay. So the hospital administrators claim that the mean, no, you're getting less than 8 patients per shift, okay? Of course, they're gonna always claim it's less, right? And so to prove their point, the nursing staff, the administrators gather information from a simple random sample of 19 nurses shift, and the sample mean is 7.5 patients per nurse, okay, with a standard deviation of 1.1 patient per nurse, okay? Test the administrators claim using an alpha of 0.025. I feel like the administrators came up with this alpha so that their hypothesis cannot be rejected. Like they fine-tuned the alpha so that, you know, the Z statistic falls just right, or the T statistic anyway. And assume that the number of patients per nurse has a normal distribution. So why did we need the assumption for normal distribution? Because we picked a sample smaller than 30. Okay, so we assume it's a normal distribution. And the sample mean is 7.5. And the sample standard deviation, not the population, the sample standard deviation is 1.1. So this tells us this should be a t-test. So we start with our null hypothesis is that the nurses are claiming, the nurses are claiming that the mean is 8 patients per nurse, but the hospital says nope, it's less than 8 patients per nurse, okay? Then we proceed and we have the significance level, that's step 2. And then we gather the data, which was already gathered for us, and we have to do a t-test in this case, okay? So we'll go ahead and do that. We'll do it in Google Sheets in a second. But in this case, the first method was to do rejection regions, which are based on critical values of the alpha. So this is a left tail test. So we need the t-score such that the area to the left of that t-value is 0.025 or 2.5%. Number of degrees of freedom is 19 minus 1, which is 18. Okay, and then you get this t-score, which is minus 2.101, okay, for the critical value. But the nurses, the sample statistic was minus 1.981, so which doesn't fall inside the rejection region, okay? And therefore, we fail to reject the null hypothesis, okay? We failed to reject the null hypothesis, okay? So in other words, and I told you they picked alpha so that this T statistic is so close to here, right? If we picked another alpha, you know, it would be inside. Anyway, but this is the point here is that this defines our significance level, the rejection region. Our sample statistic is not too extreme based on our tolerance of what we expect to be extreme. So this is equivalent to 60 heads on the coin. Yeah, this is not too extreme. We're going to be okay. So the coin, we cannot say the coin is unfair. In other words, we cannot say that the nurses are getting, you know, 8 patients or more, okay? So we can do this in Google Sheets. Let's do the p-value next. So the p-value, again, similar to the p-value we did before on the z-score, this will be based on the t-score. And this is a left tail test. You calculate the area to the left of your t statistic, okay? So the value we got minus 1.9. If it's bigger than alpha, then you fail to reject. If it's less than alpha, you reject the null. So let's build the Google Sheet with this. This will be straightforward, except we have to figure out the entire mess of what Google Sheets does with these distributions and the terrible naming conventions they have. So, excuse me, I'm going to go ahead and duplicate this, and we say mean with an unknown sigma. So those you can use on your final exam, okay, or you know, whatever research or stuff you're doing. Oh no, not all my guitars. Clicking on my photos. Okay. So mean with unknown sigma. I don't know why I put a hyphen in there. Okay, because un is not a qualifier, right? Unknown. I guess it is. Okay, so assumed mean, etc. Everything here stays the same. except here I'm not going to call it population sigma. I'm going to call it sample sigma, right? So this is our sample standard deviation. And we still have the sample size n. You can add a column for degrees of freedom. We don't need to do that. All right. And so I'm just going to punch the numbers here for the example we just did. We have 8 patients per nurse for the assumed shift. The sample was 7.4, the sample mean, and the sample standard deviation was 1.1, and the sample size was 19, okay, and the significance level was 0.025. Doesn't matter here. Now the t statistic is going to be based on, so it will be B2. I got something wrong over here. Hold on. That's something wrong. B2 minus B1 over B3 square 3. Did I mess up a number here? Hold on. I feel like I messed up one of the numbers. Okay, so 7.5. We had 7.5 over here. Okay, yep, so minus 1 point. That's our test statistic. Okay, this is going to be our test statistic. Now, we will start with the left-tailed. The right-tailed will be similar, two-tailed will be similar. We have to figure out what to use here. So the critical value is going to be the t-score such that the area on the left tail, such that the area to the left is equal to alpha. Agreed? So I need an inverse lookup on the t distribution. And with that, here's what we do. Remember? So here I need to replace this with the t inverse distribution. So this will be equal to t dot inv. Okay, we'll start with t dot inverse. Okay, and let's see. Oops, see what it does. Again, sorry about that. T dot inverse, and I need to kind of look up the help. Okay, so it calculates the negative inverse of the one-tailed d distribution, t distribution. And so yes, that would get, like, they should call it, anyway, never mind. So we will do, the probability is going to be t dot inverse, and we're going to need to put in this guy here, alpha, right? And degrees of freedom is going to be the second parameter, which is sample size minus 1. Agreed? So that gives me the t-value such that the area to the left is this alpha value. And once I put that in, I get 2.1, which is consistent with what I have on the slides here. Let me show you, 2.101. Right, so with our calculations, this is my critical value. We got the correct value. That's good. Okay. That's good. Now my p-value has to be based not on the inverse normal. It has to be based on the t distribution inverse. Okay. So let's see. Sorry, not the inverse. This is the inverse up here. This should be based on the cumulative, okay? So this would be equal to t dot distribution, the left-tailed student d distribution, and if I look at the arguments, okay, I have the t value, I have the degrees of freedom, and whether it's cumulative or not. Yes, I want this to be cumulative. In this case, the p-value is measuring the area to the left of my t statistic, okay? So what is my t statistic? It's my sample statistic here. It's going to be this one. This would be the first argument. The second argument is going to be degrees of freedom, which is n minus 1. And the third argument is going to be cumulative. Yes, this is cumulative because I'm computing the area under the curve. So it gave me a p-value of 0.0315, but my significance level is 0.025, and therefore we fail to reject, okay, because my p-value is greater than alpha. My result is not that extreme, okay? My result is not that extreme. And therefore, in other words, the probability of getting this result is acceptable to me. Because we said the alpha, the significance level in a way is saying, what probability of events are you going to say this is too extreme? we said here is 2.5%. But our result was 3.5%, 3.1%. It's not that extreme. We cannot reject the null hypothesis, okay? All right. Now, we can also do a confidence interval. So let me do that. See if I have it on the slides. Sigma unknown, right-tailed, left-tailed. Okay. Okay, so fortunately here, this is, doesn't change. So this would be, the critical value, absolute value of that, times the sample over square root of n. So that would give me the confidence interval. And indeed, it gives me a confidence interval between 7 and 7.99. And my 7.4 falls in that confidence interval. So, it's common. It's okay. That's not, it means we failed to reject the null. Okay? So this result is consistent. Now we'll do this. We can do the same thing for right-tailed and two-tailed. So let's do those based on examples. Okay, we'll go a little quicker. Method 2, p-values, blah, blah, blah. Okay. This is a right-tailed test with sigma unknown. So a locally owned independent department store has chosen its marketing strategies for many years under the assumption that the mean amount spent by each shopper in the store is $100. Seriously, what store still has that? You can go and spend $100. You go to Smith these days and you buy eggs for $1 million cents or something. And then you have all of these varieties. Oh, these are AAA large eggs that are semi-organic but caged. And then there was free range but inorganic. And I'm telling them all life is organic, right? And so no. By organic we mean that they're fed they pet them and they feed them like bottles. That's what I would imagine, a well-fed chicken or a cow. Anyway, so $100. A newly hired store manager claims that the current mean is higher and wants to change the marketing strategy accordingly. So a group of 27 shoppers is chosen randomly, so random sample. We have to assume it's normal now because it's 27 at random, and found to have spent a mean of $104.93 with a sample standard deviation of $9.07. Okay? Assume that the population distribution is approximately normal and test the store manager's claim at the 0.05 level of significance, 5% alpha. Okay? So the null, we start always step 1. So do these steps when you're doing your test or your exam. I'm breezing through those quickly, but there's still step 1, 2, 3, and 4. Okay? So do those. It will help you stay, sane. Okay. So with the null hypothesis that the average shopper spends on average $100. Okay, at the store, the manager's claim is that no, they spend more. Okay, they spend more than 100. And so that's our alternative hypothesis, that mu is greater than. This means this is a right-tailed test. We don't know sigma, therefore this is going to be a t-test. We're going to need to use t-statistics. So step 2, you need to determine which distribution to use. It's the t-distribution because we don't know sigma of the population. And the significance level is 5%. And we've already gathered the data, and we just need to calculate the sample statistic here. And so it's our information. We know that X bar, which is the sample mean, etc. And then we do a rejection region. So let's go ahead and do this. Our t-statistic is 2.8245, but the rejection region, the critical t-value, based on the significance level, alpha, is 1.706. So that's on the right. Okay, so it looks like the manager is correct. Okay, so this is our critical t-value that defines our rejection region. We say anything this extreme, we're going to say then the null hypothesis is wrong. We reject it. So from the sample, we land in this rejection region because 2.82 is greater than 1.7, obviously, and therefore we reject the null hypothesis that the mean is $100 and they're actually spending more than $100. How much? We have to run a different analysis now. Okay, we have to do something else. Okay, Same thing with the p-value. So let's go ahead and build this into Google Sheets. So here I have to do the same thing. Either I can take the absolute value to do the right-tailed, I can take the absolute value of the left-tailed, or just do it just directly from the calculation. So this would be a, we could do a right-tailed distribution here. So there's this thing, t dot inverse, hold on, t dot inverse. Okay, so now the t dot inverse always gets you the area, is based on the area to the left, okay? Not the area to the right. Now, to get that t value, we got to do 1 minus the area to the right. Agreed? The area to the left is 1 minus the area to the right. So we would do, this is equal t dot inverse of 1 minus the area to the right, which is 0.025, okay? And our degrees of freedom is n minus 1, okay? Gives me, okay, so for this problem, yep, they're exactly mirror images of each other. So let's adjust the numbers here. Mean shopper spends on average $100 per trip. The sample mean was 104.93, right? Let's double check. 104.93. Yes, 104.93. The sample standard deviation was $9.07. Okay, and the sample size was 27 shoppers. Significance level was 5%, so 0.05. Okay, then my sample statistic is 2.82. My critical value is 1.706, which is correct, 7056, correct. And then the p-value is now the area to the right. So here we did t dot distribution cumulative to the left. Over here, we need the area to the right. So there's several ways to do this. What I'm going to use is t dot distribution. And looky here, there's a right-tailed student distribution, which is really cool. So this does the job for you. It gives you give it a t-score, and it gives you the area to the right of that t-score. So we will pick that. And we're going to say that what is the, so for the p-value is going to be based on the sample statistic. So to the right of this, so let's check what other arguments. We only need the degrees of freedom, which is n minus 1. And it gave us a p-value of 0.004, which is much less than 0.05. So we definitely reject the null hypothesis. Okay, definitely reject the null hypothesis. Okay. Now, let's do, hold on 1 second. Hold on 1 second. Or p-value, let me double check my numbers that I got this right. Yep, 0.04, so we reject the null hypothesis. Okay. All right, so finally we do a two-tailed one with an unknown sigma. So this is getting repetitive, okay? We'll just do this one, and then we skim over the proportions examples, okay? So this is another example. The meat packing department of a grocery store chain packs ground beef in 2-pound portions. Supervisors are concerned that their machine is no longer packaging the beef to the required specifications. To test the claim that the mean weight of ground beef portion is not 2 pounds, so they don't know. It might be more, it might be less. They just don't know. Okay, so they want to test that hypothesis. So test the claim that the weight of ground beef portions is not 2 pounds. So the supervisors calculate the mean weight of simple random sample of 20 packages of beef. The sample mean is 2.1 pounds with a standard deviation of sample standard deviation of 0.33. Is there sufficient evidence that at the 0.01 level of significance to show that the machine is not working properly? So this is definitely a two-tailed test, we assume that the weights are normally distributed because we only have a sample of 20 packages. Okay. So first we state the null and alternative hypotheses. So the null is that what we know to be the truth, what we think is the truth, is that the mean weight is 2 pounds of these packages. And then the manager's claim, or the alternative hypothesis, the researchers in this case, it's not equal to 2 pounds. Okay, it's not equal to 2 pounds. So this is a two-tailed. We don't know the population standard deviation, so we identify the test to be a t-test in this case, using the t-distribution. Level of significance is 1%, 0.01 for alpha. Okay, so that's going to help us determine the critical values. And next thing is you just compute, gather the data, which was already gathered for us, and then we compute a t-score. You use tables, calculator, chipmunks, I don't know what you want to do, Python. It's fine. We were talking about chipmunks. We went to Deer Valley 1 year, and we kind of rented a small house in the resort there. And there were a bunch of chipmunks outside, and the kids were loving them. They were like chasing them around, like seven, 8 little chipmunks. And then there was a falcon like circling above. And I told my son, I'm going to put a sign, chipmunks here. And he was like, no! And he was like so upset with me. I was like, I'm joking. It's not the eagle's going to eat them. I'm going to eat them. Anyway, he has a great sense of humor. He can tell, sarcasm and jokes. I think it's a good ability because he gets less offended and upset at things. He always smiles, so thankfully. Okay, so the t distribution, the t statistic is 1.355 based on the data that we have. Okay, please don't report me to the Chipmunk Authority or something. All right. Okay, it was actually the first time I ever see chipmunks in my entire life, except like on TV. They're pretty cute little things. Okay. All right, finally then we draw the rejection regions. Okay, so in this case, we need to split alpha into 2 regions. We split it exactly in half. Okay, so 0.5% here and 0.5% there. Okay, 0.5% in each one of these tails. And we get these critical t values, right? They're images of each other, so it doesn't matter if you get this one or that one. They're images of each other. Yeah, then your test statistic is here. Sample statistic, if it falls in either one, then you reject the null. If it doesn't, you fail to reject the null. So in this case, it's kind of really nice, the rejection region. I like it because it's very visual, right? We fail to reject. Now for the p-value, we have to do the same thing, but we have to take the mirror images of this guy. So we put the other value minus 1.355, calculate the area to the right of this, the area to the left of that, add them up, and see together, are they less than these areas or greater than these areas? That's what we're doing. If they are greater than alpha, then we fail to reject. If they're less, then we reject. If they're less, what that means, it means this value is here, right? If they're less, it means the areas to the left and right of your statistic are less than the area in alpha, so therefore you reject it. It's another way to say that your statistic falls in the rejection region. Okay? So in this case, we fail to reject the null hypothesis. And same thing with p-values. So let's do this in Google Sheets before we take a little break. Okay? So we have to do a two-tailed test over here, and in this case we're going to need to use the t-distribution as well. Okay, so but we have to do half of alpha. So I'm going to take this left tail test. Okay, I'm going to copy it and paste it here. It's all the same numbers, but now I have alpha over 2. Okay, so that is going to give me the value to the left. Okay, the value to the left. All right, now for the meat packing plant, we have the meat packing department, we have 2.0 for the null hypothesis, and what was it, 2.1 for the sample, and what was the standard deviation? What was the standard deviation? Standard deviation was 0.33 pounds, correct? Yep, 0.33 pounds. 0.33, and the sample size was 20, and our significance level was 0.01. Okay, that's our alpha. Okay, and if my numbers are correct, yep, so get 2.86. So this is the the critical value on the left side for the t-score. The value on the right side is going to be the negative of that, the mirror image of it. Now my p-value is going to be 2 times the area based on my sample statistics. So we're going to do the same thing here, but instead of normal dot s dot distribution, we have to put t dot distribution, okay, and then we leave everything as is. Oh, and gave me a t dot inverse, and I need a degrees of freedom. That's right, n minus 1. Pardon me? Yes, because we're doing, this is a two-tailed test, right? Okay, so t dot inverse, and where did I go wrong? T dot dist, thank you, not t dot inverse. Okay, still doesn't work. Okay, so let's see, t dot distribution. Degrees of cumulative. It was missing an argument. Okay, so that's why. Okay, it was cumulative. Yes, 1. Okay, so that gave us 0.19, which is exactly what I have on my slides. So what I have on my slides, 0.19. So this is the area to the left of my negative t statistic and the right of my positive t statistic, sample statistic. Those areas are greater than alpha, or the areas in the tail. So therefore, we fail to reject the null, and we cannot say that the weights are different than 2 pounds. We cannot make that claim. Okay. As far as we know, it's still on average 2 pounds. Okay. Yes. Which one? This one? This one? Yeah. So this is where I used alpha over 2. Right? Because this is a two-tailed, so I'm taking, yeah. So let us resume. We have about 15 minutes. Let's resume. We will continue with proportions. Actually, you're going to continue with proportions. I'm just going to tell you what to do because it's the same thing. So with proportions, we go back to the z-score, z-test. Remember, we did everything with the z-test before, except the definition of the z-statistic is your z-statistic is going to be different. Instead of doing x bar minus mu over square root of sigma over n, well, it's the same thing, but now for a proportion, you use p hat, which is your sample proportion, instead of x bar, and your estimate for the standard deviation is p times 1 minus p. So this is still like a sigma over here, but for a proportion, it's p times 1 minus p. P is your null hypothesis, what you know about, what you think you know about the population, okay? And same thing, if you're doing a left tail test, your rejection region, if your test statistic is less than, the left tail value or the greater than the right tail critical value, or if it's a two-tail test, if it's not in either one of those regions, okay? And then you can also do the p-value, same thing. Once you define your sample statistic, it's exactly the same as the normal distribution tests we did before. The only thing, it's the same spreadsheet. The only thing that changes is going to be your sample statistic and also your confidence interval. You just have to make sure that you use this for your confidence interval because sigma is different now. Okay? And you don't have an entry for population sigma when you're dealing with proportions. Okay? So there's 3 examples I have on the slides. You can do those. I trust that you know how to read and write and do math. So you can do those. They're also in the textbook. They use tables, I think, in the textbook. So you can go through them. They're the same thing. I just want to jump to the variances. Okay? Oh, there's a lot of slides here. Okay. Okay, good. So we covered the proportions. We'll go into variances. All right, so with variances, it's always weird to think like, oh, what am I comparing about the variance? How much does it tell me? Eventually, you can connect the variance to what we call uncertainty, which is a very big deal when you're doing big projects and big analysis, and how you propagate that uncertainty through your workflow. But it starts as something simple, just making a hypothesis test on the variance. But instead of using the normal or t-distribution, everything applies as before, the entire idea of hypothesis testing, except our test statistic now is going to be a chi-square value. And the chi-squared, the problem though is that with the chi-square distribution, it's asymmetric, okay? So anything other than a left-tailed test or a right-tailed test, when you get to the two-tailed test, is going to be a little annoying, okay? You just have to be careful how you do that test, okay? So for the sample statistic, and again, I'll give you a nice sheet that summarizes all of these for you, which statistic to use, what formula. You calculate from your sample, you calculate a chi-squared statistic. You know your sigma for the population. You have your, you don't know your sigma. This is your hypothesis that you know your sigma about the population or the variance, sigma squared. And from your sample, you calculate the sample variance as squared. N is the sample size. And for the chi-squared distribution, you also need a degrees of freedom, which is sample size minus 1. And now the trick here is because this is asymmetric, you're going to have a different value for the left tail and a different value for the right tail. They're not going to be mirror images of each other. And for the two tail, you also have, so what you do with alpha, you still split it in half, but you're also going to have different values because for chi-squared, because it's asymmetric. They're not going to be mirror images of each other. Okay? So for the two-tailed, you have to know both of these values, chi-squared 1 minus alpha over 2 and chi-squared alpha over 2. Okay, once we show a diagram, it becomes a little clearer. We do the same thing, p-value less than alpha, then you reject the null, and p-value greater than alpha, you fail to reject the null. The only caveat is that when we get to a two-tailed distribution, it's a little bit complicated to calculate a p-value. When we had a symmetric distribution, we took the mirror image of our sample statistic and took area to the right, area to the left, right? But with the chi-square distribution, there's no mirror image of your sample statistic. So you cannot just mirror image it, take the area to the right. What do you do? So it's a little bit more involved. We're not going to cover that. We will only do a rejection region-based approach on a two-tailed variance test, okay? So you have to just manually think, is this in the tails or not in the tails? Okay, that's the only caveat we have with variances. Okay, so we start first example, left tail on variance. Suppose that your pharmacy currently buys drug A, a medication for high blood pressure. However, a new company, it's a weird statement. Suppose your pharmacy buys drug A. It's like an incomplete statement. It should be like buys drug A from a very famous manufacturer or something. However, new company says that it has a better drug for blood pressure than drug A. Okay. Both drugs have exactly the same active ingredients in them. The new company claims that its pill is better because the variance in the amounts of the active ingredients in its pills is smaller than in drug A, which is known to have a variance of 0.0009. So, although they have the same ingredients, yeah, we're going to put, hydrochloric acid, we're going to put like poisonous stuff in your pill. Okay, we're going to put this stuff, but one company has better control over its manufacturing to reduce the amount of, how clean is your drug, right? Breaking Bad. You just watched Breaking Bad, right? Have you watched Breaking Bad? Yeah, so, he made those things, whatever they're called, right? He made like 99%, whatever you guys call that name, clean. It's like, so it's the same thing, right? How much variance, how much uncertainty they have in the actual ingredients that they put in there, okay? So to test the new company's claim, a simple random sample of 100 new pills are selected, and the amounts of the active ingredients are found to have a mean of 2.47 milligrams and a standard deviation of 0.026 milligrams. Is this sufficient evidence at the 1% level of significance to support the new company's claim that its drug has a smaller variance and therefore it's better, right? In the amount of active ingredient, assume that the amounts Like, it would be cool. You go to the drugstore next time, you buy, Advil, sinus, cold, and bacteria, and whatever, right? And it has like the variance in the statistic because we buy the generic brands, right? They're like half the cost, or sometimes 40% of the cost. But what if they have more variance in their active ingredients, right? I mean, that could be something to consider. I don't know. They affect me the same. I don't care. It's like. So, but it could be that the generic might not have the same quality control, or might have better quality control. Who knows? It would be nice to have like require companies to put their variance in the like sheet thing. Okay. Okay. So we have to do first thing. We determine the. I'm very chatty today. Sorry about that. So it's like I haven't seen you in a while. I miss you guys. I have to talk more. The null hypothesis is that the variance is 0.0009, whatever units that is, maybe milligrams squared per something, I don't know. And the alternative hypothesis is that the new drug has less than 0.0009 in terms of variation. Which distribution to use? We are going to use the chi-square test and chi-square distribution because it's a variance test at the level of significance of 1%. Alpha is 0.01. Next step is you just gather the data which was gathered for us. We simply calculate our sample statistic, our chi-square statistic. And remember now, you have S squared and sigma squared here. So you might be given sigma squared and S, or you might be given variance and standard deviation, right? So be careful to square what you need to square or not, okay? So make sure you're clear about that because they've given us the variance and the standard deviation. They gave us sigma squared and S. So we need to take S squared here. That's why you get that number 0.000676, okay? And then gives us a chi-square value of 74.36. So that's our sample statistic. Now the chi-square distribution is positive. There's no negative values in it, right? It's positive, goes from 0 to infinity, right? So it's always positive. All of these chi-squared quantities are going to be positive, okay? Next, we draw a conclusion. We'll start with a rejection region. And so this is a left tail test because we have a less than 0.0009 for the variance. Degrees of freedom is 99. We don't care if the distribution is normal or not. We have a large enough sample. So these guys here in the textbook, they're using a table. And from the table, they have a little statement here that it was outside the range. So they pick the closest value for the critical chi-squared value, which was 70 on the left side, to determine the left tail. In Google Sheets, we're going to get 69 point something. So it's pretty close. And therefore, they say that the decision is to reject the null hypothesis if chi-squared, if our sample statistic is less than this value. Okay, so we look at the region. So this is the chi-square distribution for these numbers, DOF, degrees of freedom of 99. This is our rejection region at the 1% significance level, but our sample statistics falls here. So we fail to reject the null hypothesis. Okay, so in other words, the new drug, we cannot validate their claim like, yeah, you guys' drug is the same as the other one. Give us cheaper price or we're not going to buy from you, right? That's how you bargain, okay? That's how you bargain. So otherwise, go away. I'm not going to buy from you. Okay, so good. Now, with the p-value, what you need to do with the p-value is calculate the area to the left of your sample statistic. And if that area is bigger than the rejection region, then you fail to reject the null. You fail to reject the null. If it's smaller, it means your statistic is in the region, and therefore you reject the null. Okay? So let's build a Google Sheet for that. Okay, so maybe I'll just finish with this one, and then I can let you go. So let's see. Let's add a sheet over here and do variances. Okay, and we're gonna start it from scratch. Okay, so the first one is going to be assumed variance, okay, or sigma squared. This is sigma squared. If you're given sigma, you have to square it, okay? This is sigma squared. So this tells us our null hypothesis. All right, so I'm going to move this a little bit wider. And then sample variance. You can choose to define this either as a variance or a standard deviation. I just be consistent, okay? And be clear what you're doing so you don't make a mistake. And then sample size, n, okay, alpha or significance level, and sample statistic. Okay, so for this example, we had the sample, the assumed variance was 0.0009. Do you ever have a rotary phone? Have you ever, like, I grew up with, we had the loudest rotary phone. I hated people with a lot of zeros. It's like, you hate people who have a lot of zeros. So, and I hate counting numbers like 0.000009. Like there was an email, you know, W000073. Like, who picks an email like that? If you miss 1 0, you're going to send it to someone else and they might just hack you, right? Or something. So, okay, 0.0009. Okay. The sample variance, the sample variance is 0. So they gave us the standard deviation as 0.026 milligrams. So yes, those are the units for that. So in this case, we have 0.026 squared. Oops, 0. Equals 0.026 squared. Okay? Okay. Sample size was 100. Alpha was 0.01. And now our sample statistic is going to be the chi-square value, which is n minus 1, which is equal. I wish you could define variables in Google Sheets like in Python, where you just type in n minus 1, etc., instead of having to click those stupid things. Just like n minus 1, life is so hard. N minus 1. All right, so let me see. N minus 1 times s squared, right, which is this guy, over sigma squared. Agreed? Yes, so that gives me a 74.36, right? So that's my sample statistic. Now, here I'm going to do critical values. So I'm going to do a left tail distribution, and then I'm going to need a p-value and then a conclusion, okay? We'll just do this, and let's see.